In the last section, I explained the magnetic field formed by a single moving charge. In this section, I'd like to explain the magnetic field formed by a current element. So in these figures, we consider the current flowing in a straight lines and pick up the short segment, and the cross section is given by the capital A. The length is given by the dl. dl has a direction, so it becomes vector quantities. We'd like to consider the magnetic field formed by this short segment at the field point of the R. Total magnetic field caused by several moving charges is a vector sum of the field caused by the individual charges. So we have a number of the charges flowing in this short segment. The total amount of the charge in this segment can be calculated. The volume is A times dl, this is the volume, times the number density, the total number of charge. Multiply the charge of the Q, you can find the total amount of the charge in a segment, D capital Q. If you consider this is a single charge of the dq is moving to the right, then the magnetic field produced by this total amount charge is expressed this once. Drift velocity of the v sub d. The angle between the r and the v sub d is phi. Magnitude of the v cross r is expressed v sub d r sine phi. So this sine phi appears here. Then current is calculated with these equations, n number density times q is charge times the v sub d times the a. You can substitute this dq is here, and then considering the current, expression of the current, then dB is expressed like this equation, mu sub 0 over 4 pi times I is a current times the dl is the length of the short segment times sine phi over r squares. If you express the previous equations with the vector forms, I explained the dV. This is the magnitude. So we'd like to introduce directions. Direction can be found using the vector form, the dl cross r. Then divided by r, it becomes r cubed. So dV is expressed mu sub 0 over 4 pi times I times the dl vector cross r vector over r cubed. So we call that this is a law of Biot Savart. So if you want to find the total magnetic field, you have to perform the integral, use these equations. So I'd like to show you some examples to find the total magnetic field. First topic is the magnetic field of a straight conductors. So straight conductor is the lower limit is minus a to the a. Then find out the magnetic field on the x-axis. Distance between the origin to the field point is x. dB is expressed with these equations, mu sub 0 over 4 pi times I dy. dy is this length is dy, is correspond to dl, length of the short segment. dy times sine phi, angle between the y-axis to the field point. Because this is r vectors, this is dl vectors. Magnitude of r is a square root, x square plus y squares, because this is y and x. Then sine phi, you can consider this triangle. Sine phi is expressed x over square root, x square plus y squares. Then you can substitute these expressions here. And then dV is expressed mu sub 0 over 4 pi times I x dy over x square plus y square, the power index is 3 over 2. Total magnetic fields can be obtained by integrating. I'd like to show you how to integrate these equations in details. So this is the origin, this is the field point x and a, negative a. Then we consider some position of the y. Then this is theta. Tangent theta is expressed y over x. So then x square plus y squares. Actually this is equal to r squares. You can express x square plus x square tangent square theta. So it becomes x squared over cosine square theta. And for the upper limit and the lower limit, this point, this is theta sub 1, this is theta sub 2. So tangent theta sub 1 equal negative a over x. Tangent theta sub 2 equal a over x. Sine theta sub 1 equal negative a over square root x square plus a square. Then we'd like to perform this integral. B is expressed minus a to the a mu sub 0 over 4 pi I x dy over x square plus y square power index 3 over 2. This is constant quantities, and I x is also constant quantity. So we can move outside of the integrals. We'd like to change from the y to the thetas. It becomes mu sub 0 I over 4 pi x, and the theta sub 1, theta sub 2, and the dy is expressed x over cosine square theta d theta, because the y equal x tangent theta. So dy is x over cosine square theta d theta. So this corresponds to the dy. And the denominators is x cubed over cosine cube theta. It becomes mu sub 0 I over 4 pi 1 over x theta sub 1 theta sub 2 cosine theta d theta. So it becomes mu sub 0 I over 4 pi 1 over x sine theta sub 2 minus sine theta sub 1. You can substitute these quantities here. It becomes mu sub 0 I over 2 pi a over x square root x square plus a square. You have this expression. The magnetic field of infinitely long conductors. So we can use this expression we derived. Infinitely long conductor means A is go to the infinities. So this expression a over square root x square plus a square is expressed 1 over square root 1 plus x over a square. Then this term is go to the 0. B can be calculated mu sub 0 I over 2 pi x. So magnitude of the magnetic fields is depend on the distance from the conductor to the field point. So again, in this case, we can apply the right hand rules. Point the thumb of your right hand in the direction of the current. Your fingers curl around the wires in the direction of the magnetic field. Force between the parallel conductors. So current of the I. This current produces the magnetic field of the B. If the distance between the two conductors is R, then this is the magnitude of the magnetic field. Because of this magnetic field, the other wires experience the magnetic force, Lorentz force. The magnitude of the Lorentz force is expressed in these expressions. If you consider the length of the conductor is L, and then we'd like to find out the force per unit length, F over L, is expressed as mu sub 0 I prime over 2 pi R. And the direction of the force is directed toward the other current. So this means attractive force is acting between the two conductors. Two parallel conductors carrying the current in the same directions attract each other's. Parallel conductors carrying the current in the opposite direction repel each other due to the magnetic force.